Hello everyone. This is our class number 23, Multiple Regression Model Qualitative Regressors, Part 2. So in the previous couple of classes, we went over the first part where the right-hand side variables, the explanative variables, were dummy variables or categorical ones. However, in this class, we're going to look at a model that the left-hand side variable itself, the dependent variable, is going to be a dummy variable. There are many exciting applications of this model in the real world when the left-hand side variable or the dependent variable is a binary variable. For example, imagine I want to come up with a model to predict that if you guys are going to pass or fail the course, and if you pass it with what probability. Okay, this is one example. We can think of, in finance, we want to come up with models that predict if you should buy or sell, or I don't know, if you should accept or reject an application for a loan. You can think of many different applications of this model in real world. So that's what makes it really interesting. So let's begin. We are going to talk about when the dependent variable is binary. Okay, my left-hand side variable is binary 0, 1. And we're going to work with a model which is called linear probability model. We show it with LPM. So the model is a linear probability model, but the estimation engine is going to be either my OLS, weighted least square, and things like that. So we are going to do the OLS version here, but later on in next chapter, in chapter 8, when we're dealing with the heteroscedasticity, we see that OLS is not the best answer. We have to use weighted least square. And that's the topic for chapter 8. But for now, today, we say that, okay, the model is called linear probability model, but the engine is OLS. So it means that I have to check the assumptions for OLS and etc. Let's see what we have. So, and why we call it linear probability model. So again, this is a linear regression when the dependent variable is binary. Imagine I start with a model like this. This is our standard original model, y is equal to beta 0 plus beta 1 x1, and etc. Right? And now we are saying that this guy can only take two values, 0, 1, pass, fail, reject, accept, and etc. Right? So you can think of many applications of this dependent variable, which is binary, right? Now, I want to take expectation from both sides. So let's do a mathematical gymnastic and see why we call it linear probability model. Let's take expectation from both sides. So on the left-hand side, expected value of y given x. On the right-hand side, we know that these are conditional expectations. So I have beta 0. This is a constant, doesn't change. Beta 1 x1. So expected value of beta 1 x1 given x1 is going to be beta 1 x1 because we are saying that x1 is fixed. And finally, expected value of y given x. So here we have u given x. We made an assumption that it's equal to 0. So it's going to be wiped out from this part, right? So if I take expectation from both sides, I'll get to this part. Now, let's open up the left-hand side. Remember, my y variable can only take two values. Y is equal to 0 and 1. Going back to, I don't know, our review part in the first week or second week of class, what is a conditional expectation? Expected value of y given x. It is a summation of my yi multiply conditional probability of y given x. So this should ring a bell because we talked about this thing at the very beginning of the class. If you're lost here, so make sure that you review the appendices as well one more time. But basically, this is a definition of conditional expectation. What is the value of yi multiplied its conditional probability? How many y's I have? 0 and 1. So it's 0 multiplied probability of y is equal to 0 given x plus 1 multiplied probability y is equal to 1 given x. I can cancel out this part. So the expected value of y given x is the same as probability of y is equal to 1. So let me summarize it. At the end of the day, if I open up this part, it's going to be equal to probability of y is equal to 1 given x. And for short, we call it P of x, and we call it probability of success. Okay. So what I have on the left, I can go from this step to this step because y can only take two values. At the end of the day, I have something like this. On the left-hand side, probability of success. i.e. probability of y is equal to 1, is equal to the right-hand side. So we call it linear probability model. Linear because the model is linear in parameters. Probability model because this will give you something in terms of probability. So if you can calculate beta hat 0, beta hat 1, beta hat 2, and plug x1, x2, x3 for specific values, you will get something in terms of probable. So you get versus 0.68. This means that the probability of y is equal to 1 is 68%. Probability of success, 68%. Let me give you a very quick example. Imagine I am regressing. So this is, I define y as pass or fail. Actually, let me call it pass. I'm regressing, and imagine I'm looking at your class. So, well, historically, I haven't failed anyone, but let's say for fun, we have a model. So I look at your, average midterm score. I look at your average quiz scores. I look at your average homework score. So I'm regressing I look at your study hours. Well, I wish I had this number, but I don't. So I can look at the number of quizzes that you made on Canvas. So I use it as a proxy for study hours, right? At the end of the day, let's say this is my model. So I can come up with some numbers for beta hat 1, beta hat 2, beta hat 3, beta hat 4, and then I can plug information. So if your midterm average was 80%, quiz average was 70%, homework average was 90%, study hours, I don't know, 10 hours, then I'll get a number. That number is going to be, if it is 0.8, it means that the probability of passing for this guy is going to be 80%. Okay, so this is how I interpret that. And if I want to plot it, so this is important. Let's say I'm only regressing pass or fail. Again, for visualization purposes, I just look with 2 dimension if I have one explanatory variable. Let's say this is the average midterm. And at the end of the day, either you're going to fail the course when pass is equal to 0, or you're going to pass the course. Okay. We can have some observations here, some observations here as well. So what does it suggest is that for this guy, the midterm was good, but he or she ended up failing the course. Okay. This guy, the midterm was low, but he or she ended up passing the course. And the rest of them, so maybe these 2 red ones are outliers, but the rest of them are exactly what we expected. If you do good in your midterm, you expect to pass the course. If you do bad in the midterm, you expect to fail the course, right? Now, if this is the data, and again, this is the data in only 2 dimension. In real world, it's more than this dimension. And if I want to use linear probability model, what's the best fit? If the engine is OLS, this is going to be my best fit, right? So this is my linear probability model. So it says that, now let me use another color. If you give me one new observation, if for that new guy, midterm was this, the model is predicting that you are going to pass with this probability, 80%. If midterm was this, the model is predicting that you're going to pass with lower probability, okay? So this is linear probability model, but right away, we can see what's the problem with this model. The problem is that linear probability model can generate negative number and number greater than 1, which doesn't make sense at all. So for instance, it says that if your midterm, if you got close to 0 for your midterm, the model predict that the probability that you pass the course is negative 10%. Does that make sense? Absolutely not. Also, if your midterm was, let's say this is 100%. If your midterm was 100%, then the probability of passing the course is more than 1%, 100%, which also doesn't make sense. So this is the only caveat of, one of the only caveats of a linear probability model. So that's why we say that this is not the best model to use when we have the binary dependent variable. But we can control for that. We can check how many, do we have any observations here or here. If I don't have any observations in these 2 places, then I'm less concerned, okay? So we're gonna do all these things in R very quickly. But that was the gist of linear probability model. So if you wanna interpret that coefficient, beta j, that's the probability of success. In the linear probability model, the coefficient describes the effect of the explanatory variables on the probability that y is equal to 1, right? So if x increased by 1 unit, the probability of success is going to increase or decrease by beta j. Okay, so this is how we interpret that. Okay. Now let's look at an example, and we're going to stick to this example for the rest of the presentation today. Imagine this is your raw data. Okay. What do we have? We have this in LF. This is all the observations. We're talking about female. These are all women's and in the data set with these features, right? So we have in labor force. So this is going, the red one is going to become my dependent variable. So we want to see that, we want to predict that if some female with these features at the end of the day is going to participate in the labor force or not. So this is my dependent variable, Y. Can take values 1 or 0, okay? So this lady participate in labor force, so in labor force is equal to 1. This lady does not participate in labor force, so in labor force is equal to 0. Okay? So my Y variable is going to be in labor force. For X variables, we have many of them here, but the ones that I'm interested are the blue ones. You know, feel free, this is MRO's data, feel free to use all of them, or for your final project anyways, you can use any of them, any of the data sets. If you wish, I think one of the groups has already used MRO's data. So what are the explanatory variables? Number of kids less than 6. So this is 1. Oh my God, why does it, okay. Kids less than 1 plus, well, beta 0. Oh my God, I have to back out. And of course, we need a constant, we need to have a constant. I can type plus beta 1, kids less than 6, plus beta 2, kids greater than 6, plus beta 3, age of the female, plus beta 4, education of the female, plus beta 5, experience of the female, and finally plus beta 6. This is an interesting one. This is saying that basically that's husband's income. Okay, it's non-wife income. So what do you expect to see if the husband income is $1 million? So the probability that that lady participating in the labor force is going to be smaller and smaller, right? So by changing any of these variables, we want to see what will happen to the probability of this lady participating in the labor force. So that's the really, really interesting research question. So with this information, let's set up the scene. So we are going to say that we are regressing again. Either you participate in labor force or not on husband income, education, experience score, age, kids less than 6 years old, kids greater than 6 years old. And these all make sense. If you as a lady has a kid less than 6 years old, the probability of you attending the labor force is going to be increase or decrease. It's going to decrease. Okay. Now let's interpret these numbers. So how can I interpret this minus 262? Okay. We're going to say that for the woman with having kids less than 6 years old. So let's look at the data. Kids less than, so this is a discrete, so it can be 0, 2, 3, 3, 2, right? So this is a discrete random variable, right? So for every additional kid less than 6 years old, the probability of this woman attending the labor market is going to decrease by this unit. What's the unit? It's percentage. So the probability of this lady participating in the labor force is going to decrease by 26.2%. Does that make sense? Well, in my opinion, absolutely. If you have 3 kids less than 6 years old, so your probability of you attending the labor force is going to decrease dramatically. So the model is suggesting that it's going to decrease by the order of 75-ish%. Okay. Let's interpret one other and then move on. So let's interpret education. For every additional years in education, the probability of that lady attending the labor force is going to increase by 3.8%, holding everything else constant. Does that make sense? Nice, right? Okay, I'm allowed to say something like this because remember, I don't see education anywhere else. If I had education somewhere else, make sure you have to take derivative first and then interpret that, okay? Okay, you see interpretation is super easy. And let's look at this funny one as well. The units, of non-wife income or husband income. Well, let's call it partner income because we don't know if it is husband. So let's call it non-wife income. Okay. The unit is in $1,000. So it says that for every additional $1,000 that the non-wife is bringing to the house, the probability of the lady going to participate in the labor force is going to decrease by literally 0.3%. So if you bring $1 million, so it's 1,000 multiply this number, the probability of you participating in the labor force is going to decrease by 3.4%. Which is okay. I think it should be higher than that, but the data does not support that. Okay. Again, this is fun. Econometric is fun. You have some belief, and then you throw data at it to interpret that. Okay. Let's visualize this thing in 2-dimension. Look at that. I have 1, 2, 3, 4, 5, 6. I have 7 explanatory variables. There's no way I can visualize it in 2-dimension. The only way that I can visualize it in 2-dimension is that I assume 6 of them to be a fixed number and look at the 7th one, right? Because originally I have to go to the 7th dimension and look at this, whatever weird shape it has in terms of regression. But here, again, for just fun or some having learning experience, let's go ahead and fix a bunch of them and look at what will happen. Imagine you're interested in the education versus the probability of participating in the labor force, right? I have to fix all the other explanatory variables to some numbers. I'm going to fix them at their some numbers. So this is a graph for when the husband or non-wife income is 50,000, experience is 5 years, age is 30, number of kids less than 6 is 1, number of kids greater than 6 is 0, right? Fixing these numbers, if I go back to the slide, if I fix all these numbers, so I can replace them by some intercept at the end of the day. So I will end up with education only, right? So I will end up with, okay, in labor force is equal to some constant, theta 0 plus 0.038 education, right? And this number is going to be different. This is what we're plotting on the next slide. And this is what we're plotting. Look at that. The slope is going to be the one that I exactly told you. The slope is not going to change, right? 0.038. Then the intercept, this is going to change depending on different values that you pick here. Okay, but let's say this is what we have. So this is our prediction at the end of the day. We know that the real values are going to be either participate in the labor force, this is the real Y's, or not participate in the labor force. Okay, we are using OLS, and OLS is going to tell us that this is the best fitted line. Look at that, this is the best fitted line that minimizes the residual R-squares, and that's it. So what's the thing that we don't like about this is that the model is saying that if education is less than 3.84 years, then the probability of that lady participating in the labor force is negative. This is nonsense. It also suggests that if education is greater than this number, the probability is going to be greater than 1. This is also nonsense. Now, should I be worried about that? We can do a couple of things. We can see how many observations I have here, how many observations I have there. So let's do that. So negative predicted probability, but no problem because no women in this sample has education less than 5. So our data is going to start from here, 5. So I'm not worried about these negative numbers. Poof, good, right? What about this one? The maximum level of education in the sample is 17 for that given case, for this given case, okay? And this leads to predicted probability of participating in a labor force of only 50%. So you're here. 17 is the max, and the probability of participating in the labor force is 50%. So the education is between these two, 5 and 17. And between these two, the model is doing a decent job, giving you back some probabilities for this given data. If I use another given data, so the numbers are going to change, right? Okay, so we are not worried about the caveat of LPM here that is going to produce negative number or probability greater than 1. Logistic regression is going to solve this problem, but that's the topic for chapter 17. here we're going to say stick to this model, but we need to be careful that our predictions are not going to be negative or greater than 1. For those of you guys who want to do a project using linear probability model, you should be careful. At the end of the day, I want you to look at your prediction. If the number of predictions that the model is making less than 0 or greater than 1 is large, let's say it's 50% of the data, then you should not use this model. Okay. But for the data set that you guys picked, like Ambrose or the other, I had another group that they were thinking of LPM model, you're safe. So I've already checked these data sets. Your predictions are not going to be less than 1% of the data has a prediction of -1 or greater than 1. You can get rid of those data. Okay. Okay. Now, in terms of time, how are we doing? Very good. Okay. So let's see what's the goodness of fit for these models, because look at that. So if I go back to that pass or fail, and then this, R-square is not a good measure for goodness of fit anymore, or even adjusted R-square. This doesn't make sense because, again, we are talking about all the zeros and ones. So we have to say something else. We have to count the misclassification. We have to count. So for instance, the model says that passed or participated in the labor force, but in reality, she didn't participate. So this is misclassification, right? So we need to count the number of correct calls of the model and divide it by the total number of observations. So this is the measure that we call it accuracy, and we're going to use it. Okay. So let's say, again, there are three, in terms of goodness of fit, we're going to look at 3 measures. Percent correctly predicted. The true model, the true data was pass, and the model said pass. Percent correctly predicted when the model was 0, well, the true value was fail, and the model also said fail. And finally, the overall correct prediction, we call it accuracy. Okay. So let's see, this is again, intuitively, it's very easy. And I have replicated this table in R, so we're going to go over it very quickly. All these numbers we have replicated, so you know what we are doing, how we can generate these things. So let's say I have 20 observations, right? So I'm looking at 20 observations from Ambrose data, and these are my x's, so these are given. This is my y variable. Remember, y in the data set can take 2 values, 1 or 0. So the green ones are the ones that the actual value is 1. The red ones are the one that the actual value is 0. Okay, so y is 1 here, y is 0 here, right? Then if I use LPM, the output of LPM, we just said that the output of LPM is some probability number, right? So for first observation, the model is predicting that with 99% probability, she's going to attend the labor force. For 10th observation, the model is predicting that with 76% probability, she's going to attend the labor force. Observation number 15 is saying that this lady with 64% probability, she's going to participate in the labor force. And then finally, observation 12 is saying that only with 29% probability, she's going to participate in the labor force, right? But if you want to compare apples to apples, I mean, by apple to apple, I mean y versus y hat. It's not fair to compare 0 ones with these numbers, right? So this is what I mean by apple to apple, comparing apple to apple. So I have to do one extra step, and that extra step is that we're going to come up with a subjective rule, and this rule is subjective. It's literally subjective. But what is the best number that I can use? I'm going to say that if y hat is greater than 50%, if the probability of success that the model is predicting is greater than 50%, call y hat is equal to 1. If it is less than 50%, call y hat is equal to 0. And this is subjective. This 50% is subjective. And I personally believe, again, if it's on me to do this regression analysis, I'm not going to use LPM. But because you guys, the rest of it is beyond the scope of the class, you should have to use the LPM, right? Okay. Again, We know that the answer is not LPM, the answer is logistic regression, but for this course, that our hands are tied, we have to stick with that rule, but be careful about that subjective rule. So here in this example, we're going to use that rule of thumb that if y hat is greater than 50%, call it 1. So let's look at that. 1, 1, 1, 0. Can you see that? Because it's less than 50%. 1, 0, 1, 1, 1, 1, 0, 0, 1, 0, 1, 0, 1, 0, 0, 1. Okay. Now, I want you to pay good attention. These ones, the green ones, the true value was 1. In the real data, they are all the women that participated in the labor force. What are the right calls? So the model said that lady number 1 participate. This is a right call. Number 2 participate. Right call. Right call. Wrong. So let me use red. And just for wrong calls. So wrong call. Wrong call. Can you see that? So I have 2 wrong calls from the first. So if I want to say that the percent correctly predicted, so how many observations I have? 10. How many of them are correct? 8. So what's the percent correctly predicted? 80%, right? Let's do for the percent correctly predicted when y is equal to 0. So what are the right calls? The model says the true value is 0, model says 0. So this is right. So again, as the previous one, let me call the wrong calls. So this is a wrong call because the true value is 0. The model said that the lady participated in the labor force. This is wrong, 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 and wrong. So what is the percent correctly predicted? So 4 of them are incorrect, 6 of them are correct, 60%. So 80%, 60%, again, we need to count these observations, right? And we're going to do it in R. So I'm going to walk you through how we can calculate this thing. This is very easy. Okay, there is no built-in function in R, but we need to construct that function. But it's an easy job. You should simply count and using the filter function. Okay. Now, finally, this is what we usually use, overall correct prediction. We call it accuracy. And basically, it counts the number of correct calls. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I have 14 correct calls out of what? Out of 20. So 14 out of 20, 70%. So this is the measure of goodness of fit for a binary dependent variable. We're not going to use R-score or adjusted R-score. This is the measure that we use because we have to count the number of misclassification at the end of the day. All right, so a couple of more slides, advantages and disadvantages of linear probability model, and then we're done. So what are the disadvantages? We already talked about one of them. Predicted probabilities may be larger than 1 or smaller than 0. So this is a disadvantage of using linear probability model. How can I deal with that? So I need to count the number of predictions that are less than 0 and greater than 1. If it is less than 1% of the data, it's fine. We're going to throw away that 1% of the data and stick to the model. Okay, so this is no big deal. So marginal, what else? Marginal probability effect, sometimes logically impossible. Having 4 kids under 6 age in the previous example. Okay, so the same story. So let me go back and tell you what's going on here. Do you remember having less kids, kids less than 6 years? It says that you cannot literally calculate the marginal probability for this variable if it is even for 4 kids. So if I have 4 kids less than 6 years old, what's the probability of participating in the labor market? 4 by minus 2.6 is greater than 100%. So it's going to say that the probability of attending in the labor force is going to decrease by 100-something%, so which doesn't make sense. So that's why it says that calculating the marginal probability is not doable. So this is this bullet point. Marginal probability effect sometimes logically impossible. Okay. Then look at this one. Linear probability model is necessarily heteroscedastic. So this is a big deal with the LPM. And let's see why this is a big deal. If it is heteroscedastic, it's a violation of assumption number 5. So I need your background in the statistic. So if your random variable can take two values, 0, 1, so what's the distribution? It's going to be a Bernoulli random variable, right? Because it's pass or fail. So for a Bernoulli variable, with the probability of success equals to P, what is the expected value? The expected value for that Bernoulli variable, well, let me use Y here, not confuse you. So I know, again, this is a statistical fact that we should know from our statistic background. The expected value of a Bernoulli variable, let's say my Y is a Bernoulli variable, is going to be equal to probability of success. And the variance of a Bernoulli variable is going to probability of success multiply 1 minus probability of success, or P multiply Q, probability of success multiply probability of failure. So this is a statistical fact. If you're wondering where it's coming from, this is not the right place. You have to review your statistics classes. But we know that it's going to be the case. And we already showed that this P probability of success is the probability of Y equals 1 and X. So we just basically replace it with PX. Look at that. We are saying the variance of Y given X. So this is the problem. We're saying that the variance of Y given X is equal to probability of X multiply 1 minus probability of X. It's a function of X. So this says that as for different values of X, your variance is going to change. We don't like it, right? So we wanted to have homoscedasticity. We wanted to have variance of Y given X is constant. This is homoscedasticity. But we know for a fact that the variance of Y given X, if Y is binary, it's not constant. That depends on different values of X. So by construction, LPM model is violating assumption number 5. If it is violating assumption number 5, it's a disaster, right? I cannot trust on the variance. I cannot come up with a closed form solution for variance. Well, I can, but I cannot trust that number. Variance of beta hat J, then I cannot use T or F. I cannot rely on these numbers. I cannot rely on confidence intervals. So it's a big problem. We have to fix it, okay? So we have to fix it. How we fix it? Watch the next video, which is chapter 8, heteroscedasticity. So whenever we have linear probability model, we need the, well, let me show you the quick answer. We cannot use OLS. We have to use weighted least square. Okay, so this is the short answer. But watch the next video. I go over full explanation how we can handle this problem. So heteroscedasticity, consistent and standard errors needs to be computed. Again, this is chapter 8 material. So these are the disadvantages. What is the advantage? It's simple. Linear probability model is very simple, easy estimation and easy interpretation. Estimated effect and predictions are often reasonably good in practice. Again, this is an easy model to work with. Final slide. So let's talk about policy analysis and program evaluation. So this is just one example from the textbook. For instance, we are interested in a question like this. Are non-white customers discriminated against when they're applying for a loan? Discrimination in loan approval. And again, sadly, that's the case. There are some sad events in our world that we're living. Again, even in 2020, you think that the data should not support these ideas of wage discrimination, race discrimination, but it is sad that we still see these things. And I strongly believe that we have to do something about it, right? Anyways, so let's say you're interested in, so my left-hand side variable is approved or not. So it's a dummy variable, 1, 0. It's a binary variable, okay? We are regressing this approved or not on some race dummy. And for non-race dummy, I just use non-white. I want to see if you're non-white versus anything else, okay? Basically here, because I don't have any other dummy, so it means that, so it's only 2 classes, non-white and white. Then income, wealth, let's control for income, wealth, and credit rating. Okay, so it is important to control for other characteristics. Do you remember, in last class, we were not controlling for, we only said that, okay, we regress wage on female. And the effect of wage discrimination was huge. But when I controlled for more explanatory roles, the impact get less and less. So it is important to control for other characteristics, okay? And also think of this idea that omitting important characteristics that are correlated with the non-white dummy variable will produce spurious evidence of discrimination. Okay, so basically it says that maybe there's something here that you're getting rid of it, and that thing was highly correlated with your race dummy, and it's going to make this coefficient bias. Okay, so the reason that I put it here is that I just wanted to emphasize, we talked about it when the right-hand side variables were dummy. Now let's talk about it when the left-hand side variable is dummy. Or we have dummies in both sides, left-hand side and right-hand side. So whenever you have something like this, make sure you control for enough explanatory rules. All right, so we're done with the theory part of this chapter. All right, this was our chapter 7, another important and interesting chapters from the Woolder's textbook. And the only way, in my opinion, for you guys to learn these things very deeply without memorizing necessarily stuff is to practice them in R. You know, have RStudio open in front of you, go over the slides, try to implement whatever you see on the slides in R, and try to play around with it, write down your questions, bring your question into the classroom, and we will discuss it together. Okay? So again, in my opinion, if you want to learn it very deeply, please keep practicing it R. Without practicing it for yourself, you're not going to learn it. All right, so until then, see you in the classroom.